Good morning, guys. We are going to be working on module 3.3 today. And this one is on linearity and continuity of graphs. So let's look at our learning target. I can determine whether functions are continuous, discrete, or neither. And I can determine whether functions are linear or nonlinear. Now, before we get into module 3.3, I want to quickly reflect on what we've done in module 3.1 and 3.2. So let's quickly talk about functions. So when in functions, we have the x, all right? So this x is also called the input, right? What we are putting in to an equation. So the input, it's also called the domain, right? And the input is the independent variable. So it's also called the independent variable. Okay, so these are all the terms for the input or x in a function. All right, when I say f of x, this now is giving me the y. Okay, f of x, this is nothing but from the input I'm getting an output. So f of x is nothing but the y. Okay, and that's also called the output. It's also called the range. And in order to find y, which is f of x, I have to depend on x. So that is why it's also called the dependent variable. Okay, so this is a refresher, and once again we've talked about to find the f of x, we can use mapping, graphing, tables, equations, etc. All right. Another thing I want to quickly show you once again is to know if a graph is a function or not. So in order for me to see if a graph is a function or not, it has to pass the vertical line test. Okay, it has to pass the vertical line test, and this can be used to determine whether a graph represents a function. If we draw any vertical line through a graph and it intersects the graph only once, then it is a function. But if it is intersecting the graph more than once, it is not going to be a function. So let me show you some quick examples. Again, a reflection of what we've done in module 3.2. So let's look at this. If I give you something, let's say y is equal to x, and that's my equation. Okay, so I know if y is 2, x is, so if x is 2, y is 2. If x is 0, y is 0. If x is 5, y is 5. So it is going to be a straight line in this case. So if I have a graph which is something like this, okay, y is equal to x is going to be a straight line like this. Okay, that's literally what I'm going to be getting. Okay, now if I get a line like this, for me to see that whether this is a function or not, all I have to do is a vertical line test. So if I take a straight vertical line and I put it like this, this is the vertical line test. So let's look at the graph. How many times is it cutting that graph? It's just one time over here, right? Just one time here. It doesn't matter where I put the vertical line. It's going to cut through the graph one time. And so yes, that tells me that this is a function. All right, let's do another drawing. And let's say I give you y is equal to x squared. So if I give you y is equal to x squared, I'm going to get a graph which looks like this. Okay, it's going to go in this format. All right, so I'm going to get a graph which looks like this. Now let's look at this graph. Does this pass the vertical line test? So I'm going to draw a vertical line here. Is it cutting through the graph just once? Yes, it's cutting through the graph just once. It doesn't matter where I put it down, the vertical line, it's going to cut through the graph just once. So that is telling me that this is a function. All right, let's do another one. And let me give you a graph which is telling me x is equal to y squared now. Okay, so in this graph, if I have this and I have this, okay, I'm going to end up with this. I'm going to end up with a graph that looks like this. Now let's look at the vertical line test. So if I put a vertical line down, is it intersecting that graph just once? No, it is intersecting that graph in two places. So over here and over here. And because of this, because it's intersecting in more than one place, this is not a function. Not a function. All right. Just going to draw out two more for you. What if I give you a graph that looks like a circle? Let's say I have a graph which looks like this. Okay, so let me draw the vertical line again. And if I draw the vertical line, is it intersecting in just one place? No, it is intersecting here. This is one, and here's another one. So therefore, this is not representing a function. All right, and so two more examples. I can give you a graph which looks like this. So if I have a V, let's say I have a graph which is like this. Now, when I look at this one, it doesn't matter where I put the vertical line. It's intersecting only in one place, here. So yes, this is representing a function. Let's say I make another graph and I do something like, I'm going to draw it here, okay? So here's another one. And I make something like this. So let's look at this one. What's happening here again? If I go like this, it is intersecting only in one place. So this is representing a function. And then let's do one which is going like, let's say I do something where my graph is going like an S. This is my graph. Now let's do the vertical line test. So if I take a vertical line and I put it like this, is it intersecting only in one place? No, look, this is the first place, this is another place, this is another place. So it's representing in three different places or three different points. So that's why this is not a function. And let me give you one last one. This is just to refresh your memory as to what is the vertical line test so it makes sense. All right, and so here's another one. If I have a graph which is like this, all right, and my graph is going like this. Let's say if I have a graph like this. Now, let's do the vertical line test. If I do this, is it intersecting in more than one place? No, it's only intersecting in one place. So therefore, this one is a function. So this is a quick refresher of what the vertical line test is before I continue model 3.3. All right, so now let's get into discrete and continuous functions. And I am going to write out what each of these means over here. So I made a little table. And let's look at what is a discrete function. So a discrete function is one in which the points are not connected. Points are not connected. Okay? Points are not connected. And I'm going to show you a graph in a little bit so you can understand what that means. All right. The continuous functions, points are connected to form a line or curve. So points are connected to form a line or curve. And in the last one, neither discrete or continuous. Some points are connected by a line or curve. Okay, some points are connected by a line or curve. And it is, but however, it is not continuous everywhere. Okay, so but it is not continuous everywhere. So once again, in a discrete function, the points are not connected. In a continuous function, points are connected to form a line or a curve. And in neither discrete or continuous, some points are connected by a line or curve, but it is not continuous everywhere. So in order for you to understand what I just said, I'm going to just take you to my whiteboard where you can look at an example of some graphs which are explaining each of these. So let's look at the discrete function. And this is the one that I had just said that the points are not connected. These are not connected. Like look in the continuous one. It is connected. So it can either be a straight line or it can be a curve. So in this case, they are connected and this is forming a curve. And so that's a continuous function. And in neither discrete nor continuous, we said that some points are connected by a line or curve, but it is not continuous like this. Okay, so that this one is neither discrete nor continuous. Just looking at this. All right. Now, when I look at discrete function, we have the domain, which is the x. This is going to be a set of individual values. And the range is also going to be a set of individual values. So these are individual values in this, the domain and the range. So the x and the y are both going to be your individual set of individual values. All right, let's look at the continuous function. In this, the x, which is the domain, is going to be all real numbers. All real numbers. Okay? So, remember we've done that, what real numbers are, rational and irrational numbers. They are all real numbers. So, this is going to be all real numbers, and the range is going to be one interval of real numbers. So, one interval of real numbers, and we're going to get into this just now. Okay? And let's look at the last one. In this, the domain and the range are both varying. Okay, so this varies. So once again, domain is x, range is f of x. All right, so function of x, which is your, again, domain is your input and range is your output. And domain is your x, range is your y. F of x is y. All right, so this is just a quick visual of what this lesson is going to be covering. Okay, so now let's look at this problem. We are determining the continuity over here, and that's what this is, determine the continuity. And so books, the bargain book barn sells young adult novels on a sliding scale. That is, the more books you buy, the cheaper they are. Let f of x model the store's prices for given quantities. So this is modeling, this is f of x, is modeling the store's price for given quantities. And is f of x discrete or continuous? And we're going to explain our reasoning. So you can see for one book, we have $1.50. For two books, we have $2.90. For three books, $4.30. For four books, $5.70. $5, we have $7.10. So I'm going to show you the graphing of this, and then we can discuss it. Okay, so if I show you the graph of this, look, and we just said that for one book, this was for $1.50. For two books, we have $2.90. For three books, $4.30. Four books, we have it for $5.70. Five books is going to be $7.10. So the graph is made over here. But as you can see, we are using the table and context of the situation. The quantity and price correspond to ordered pairs, like we said, one for $1.50, two for etc., right? So this can be graphed. Now, remember, books are not sold in fractional parts. Either you have one book or you have two books. No manufacturer is going to say, oh, let me tear off half the book and give it to you. So that is why this line cannot have that continuity. You cannot connect the dots, because I cannot have one half of a book. Does that make sense? Because you can buy either one book, you can buy two books, you can buy 10 books, but I cannot buy 4.5 books. Nobody's going to tear off half a book and give you. So as you can see, that is why we do not connect these dots. All right, and so the points should not be connected, and because they are not connected, what is this one? We just talked about it, that when points are not connected, it is going to be a discrete function. This is a discrete function. Okay, so again, because the domain and range are sets of individual values. Okay, so domain and the range are sets of individual values, and that is why this is a discrete function. All right, so let's go ahead and look at some more graphs, and let's look at these two, and we're going to talk about what kind of a graph is it. Okay, so let's look at the first one. All right. If I look at the first one, is it passing the vertical line test? Absolutely, right? Because wherever I draw a line vertically, it's going to cut that graph only in one place. So absolutely, it is passing the vertical line test. It is a function. Now we are looking at whether is it discrete, is it continuous, or neither. So f of x, as we can see, it's graphed with a single curve. It is a continuous function. The domain and range are both all real numbers. So this one is a continuous function. This is a continuous function. All right. Let's look at B, g of x. And if I'm looking at this one, I can see that because g of x has continuous sections, it does have continuous sections, okay, but it is not a single line or curve. For it to be continuous, it has to be a completely single line or curve like this one, okay, but it is not a single line or curve. And it is neither discrete nor continuous, because in discrete, what do we have? We have the individual sets, right? And so, in the individual one, we are not connecting them. So in this one, as you can see, that the domain and range are intervals of values. So this one, it is neither, this is neither discrete nor continuous. So it's neither discrete nor continuous. Okay, by just looking at the graph. All right. So let's go on to this problem. So it's asking on this one, what kind of a graph is this over here that I just showed you? So let's look at this one. As we can see, is it connected? It's asking whether f of x is discrete, continuous, or neither. So first and foremost, is it connected with a line or a curve? It is not. Is it having separate areas of connection? No. Those dots are not connected with a line or a curve. So this is going to be a discrete function. This function is a discrete function. Okay? So, because what is happening? The domain and range are sets of individual values that are provided. So this is a discrete function. All right? So, let's go on to a problem, which is here. So apply discrete and continuous functions. And let's look at this one. Detective. As a private investigator, Tia charges $25 per hour for any amount of time up to 8 hours, and then a flat rate of $250 per day. Use the graph to determine if the function that models the situation is discrete, continuous, or neither. So, if I look at this graph, is it discrete? No, because the function is not made up entirely of individual points. It's not made up of individual points. Okay, so it is not discrete. Is it continuous? Can I draw a straight line or a smooth curve on this graph? No, I cannot draw a straight line or a smooth curve on this graph. So this is not a continuous function. All right, and then, so if it's not discrete, it is not continuous, so therefore it is neither. Okay, so yes, this is neither, this one, because it is not discrete and it is not continuous. So that is a discrete function. All right, so here we have another question, and this is talking about plant circadian rhythms. All right, so circadian rhythms are cycles of behavior that occur every 24 hours based on a day-night cycle. One aspect of a plant's circadian rhythm is the percentage of its flowers that are open or closed. If f of x is represented by the curve, then is f of x discrete, continuous, or neither? So, let's look at this. These are all connected with a curve. Okay, and where does that happen? It happens in a continuous function. So it has the curve going in a rhythmic manner over here. So it's represented by the curve. And so this function is a continuous function. All right, so let's talk about this really quick. Linear and non-linear functions. Okay, so a linear function is a function that has a graph that is a line. That's why remember, it's got line in there. So that's a linear function, okay, because it has a graph that is a line. And I always want you to look at this part so we can see that, yeah, because this part. So it's telling me that a line is in that graph. If the domain of the function is all real numbers, then the function is continuous. And then a linear equation can be used to describe a linear function. And linear equations are often written in standard form. So, what is the standard form of a linear equation? It is going to be ax, and this is a standard form of a linear equation, all right, plus by is equal to c. Okay, so this is the standard form of a linear equation. This is a standard form of a linear equation. All right, so if I look at this one, where a over here, a is greater than equal to 0. All right, and b, so where a is greater than equal to 0, a and b are not both 0, because then that would be 0 times x, so 0 times y would make it 0. Okay, so where once again a is greater than equal to 0, a and b are not both 0, and a, b, and c are integers with a greatest common factor of 1. So if I give you an example and I say 2x plus 5y is equal to 7. If I give this to you, then I can look over here. This 2 is A, 5 is B, and my 7 is C. Okay, so I just wanted to show you what a linear equation looks like. Once again, the standard form of a linear equation is in the form ax plus by is equal to c. And that is how you write out a linear equation. A nonlinear function has a graph with a set of points that cannot all lie on the same line, and that is why it is nonlinear. It's not going to lie on that same line. In a linear, it's all going to lie in the same line. That's why it's linear. But in a nonlinear, it will not lie on that same line. Okay? And so an equation that represents a nonlinear function cannot be expressed in this form. This is only for linear equations. For nonlinear, it cannot be expressed in this form. And the function values of a linear function change at a constant rate for every equivalent change in the x values. The change in the function values for a nonlinear function will vary for equivalent changes in x. All right, so let's do a problem, and we are looking at, is it a linear or is it non-linear? Okay, so let's say I give you In order for me to see if this equation y is equal to 4x squared minus 2x squared plus 3x minus 5 is an equation for a linear or nonlinear function. So the first thing we are going to do in this case is we are going to simplify this equation. So let's start with the original equation, and it's telling me y is equal to 4x squared minus 2x squared plus 3x minus 5. And then I am going to first, of course, I have to follow the order of operations, and I am going to, do the exponent first. Okay, so therefore I get y is equal to 4x squared minus, what is 2 times 2 is 4, and x times x gives me x squared. Okay, plus 3x minus 5. Now, what is 4x squared minus 4x squared? Is 0. Any number, you take the same value and you subtract from it, you are going to end up with 0. So this gives me 0 over here. So y is equal to 0 plus 3x minus 5. So ultimately, what do I have when I'm simplifying? Y is equal to 3x minus 5. Now what I'm going to go ahead and do is I'm going to take that simplified equation, and if you remember what I just taught you earlier, we are going to see if it is falling in the same format, which is the standard form of an equation, of a linear equation, which is, we've got to write it in this format, ax plus, what do we have? By is equal to c. So this is my standard form of a linear equation. So let's see if we get that after solving this. So we have y is equal to 3x minus 5. I'm going to write that here. Y is equal to 3x minus 5. And I am going to now move the 3x to the other side. So for me to do that, I have got to subtract 3x from both sides using the subtraction property of equality. And I get y minus 3x is equal to negative 5. Y minus 3x is equal to negative 5. And then I'm going to simplify, and I am going to write it in the format. I'm going to change this sign and this sign. Okay, so this is going to be 3x, change this sign, minus y is equal to 5. Okay, because we are multiplying each side by negative 1. Multiply each side by negative 1 in this step. And so then I end up with, what did I get over here? I got y is equal to 3x minus 5. So, because 3x minus 5 is in the form of ax plus by is equal to c, where this is a, okay, and then I have b is what? What is the coefficient over here? It is negative 1. So that this one is b. So a is 3, b is equal to negative 1. And then what do I have for c? C is equal to 5. And so this is a linear equation. This is a linear equation because we can write it in that format. Okay, let's do another one to see if it is linear or not. Let's look at this one. And same thing, we are going to go ahead and try to put it in the format that I just told you was the standard form of a linear equation. Ax plus by is equal to c, and we are trying to get to that format. Okay, ax plus by is equal to c. All right, and there's my standard form of a linear equation. So we are going to go ahead and start simplifying this. We take the original equation, which is y is equal to 3x cubed minus x cubed plus 3x plus 6. And so what is 3x cubed minus x cubed? So I've got 3x cubed, x cubed, remember the coefficient of x cubed is 1. So minus 1x cubed, and that gives me y is equal to 2x cubed. Y is equal to 2x cubed plus 3x plus 6. All right, and then next I am going to subtract 2x cubed and 3x from each side. So I am going to get y minus 2x cubed minus 3x. I'm going to subtract that from both sides, okay, is equal to 2x cubed minus 2x cubed, okay, and then I have plus 3x minus 3x, and of course I have my plus 6. So I'm trying to get rid of this. Remember, subtraction property of equality. And so now what am I left with? I'm left with y minus 2x cubed minus 3x is equal to 6. And so we are again going to multiply each side by -1. Going to multiply each side by -1. And what am I left with? So I get 2x cubed, because I am multiplying this all here. I am multiplying by -1. And so -1 times negative times negatives gives me positive. So I have 2x cubed plus 3x minus y, okay, is equal to -6, because everything here is multiplied by -1. So let's look at this one. Is it in the form ax plus by is equal to c? It is not. And so therefore, as you can see, this is definitely not in this format. So this is a non-linear equation. This is a non-linear equation. Okay. Let's look at this. And we've got functions in the table form over here. So, soccer. Selena kicks a soccer ball. The height of the ball after each half second is recorded in the table. Okay? Is the function that models the height of a ball a linear or non-linear function? So let's look at the table. And during the first half, the ball goes from a height of 2 feet to a height of 28 feet. So this is an increase of how much? This is an increase of, if it's going from 2 to 28, this has increased by 26 feet. Right? During the second half second interval, the ball is going, so over here, where is it going? From 28 to 46. And this is an increase of how much? This is plus 18. So here it increased 26 feet, here it increased 18 feet, and because the change in the height varies over the two equivalent intervals, the height of the soccer ball must be modeled by a non-linear function. If it was a linear function, it would be going exactly the same amount, it would be plus 26, 26, 26. But because it's going at those different intervals, the height of the soccer ball must be modeled by a non-linear function. Okay, so let's go ahead and look at two more examples and see whether it is linear or non-linear. So let's look at the first one. Determine whether the values in each table are best modeled by a linear or non-linear function. Okay, now I need you to realize that when you are seeing that, that something is going up, it's going from negative 15 to negative 3, and then 0, and then 3, and then 6, and then 9. I need you to be mindful that there may be values in the x that are missing. So the first step I would suggest before you say that it is nonlinear, just by looking at that, is you want to put in all the values for that table to make sure that it is going up in the correct form. So I just have drawn out a table really quick for you to understand that the first one will be a linear function because there are certain values that have not been added on. So don't assume that it is jumping from erratically from negative 15 to negative 3 and then to 0 and then 6, because look what's missing on x. From negative 5, it has gone to negative 1. So you need to understand that we have negative 4, negative 3, negative 2, all that in between. So I've just drawn out a table really quick to show you what I mean. So let's look at this. So we have, if we had negative 5 times 3, we got negative 15. Negative 4 times 3, negative 12. Negative 3 times 3, negative 9. Negative 2 times 3, negative 6. So look, these are all the values. So it's going in a set method, in a set format. And so in every thing that I'm going down, it is increasing by 3 constantly. So as you can see, this is all, what am I getting over here? I am getting, look, plus 3, plus 3, plus 3. So the same thing is going on overall. So, it's the same here. Look, it's the same rule that is going on. So because of this, the first one is a linear function. This is a linear function. Okay? Let's look at the second one. Now this has all the values 0, 1, 2, 3. 4 is missing, and that's fine. But as you can see, it is not going with the same format over here like it was here. Okay? And so because of this, this one is non-linear. This is a non-linear function. It has to follow the same rule, just like over there. So the first one was linear, and which is this side, and then the second one is non-linear. Okay, so that's what these tables are modeling. Let's do one last problem. So here's the last problem. Fernando uses a garden hose to fill his empty pool. The table shows the amount of water in the pool after every 5 minutes. So first we are going to determine linearity, and then we are going to graph it. So let's see if there's a pattern involved. Okay, so in 5 minutes, 60 gallons. In 10 minutes, 120 gallons. So if I'm looking at this, what is the growth that I am seeing over here? Okay, so look, how much has that increased? So the amount of water in the pool increases by 60 gallons during the first 5 minutes. It also increases by 60 gallons during each following 5-minute intervals up to your 25 minutes. So this is all plus 60, plus 60, plus 60, plus 60. All right, so because the change in the amount of water is constant for every equivalent interval of 5 minutes, the numbers in the table can be modeled by a linear equation. Okay, so this can be, or by a linear function. Okay, so let's go ahead, and I'm just going to show you the graphed version just to save time. And here is the graphing of that. And as you can see, the points on the graph, they can be connected by a straight line. It can be connected by a straight line. So as you can see here we have 5 minutes 60 gallons, in 10 minutes 120 gallons, 15 minutes 180 gallons, 20 minutes we have 240 gallons, 25 minutes we have 300 gallons. So as you can see, the points on the graph can definitely be connected by a straight line. And that's basically what module 3.3 is. And it's just talking about the linearity and the continuity of a graph. Please remember the 3 important things that we have learned are the 3 different types of functions. And again, in a discrete function, the points are not connected. In continuity or in a continuous function, points are connected to form a line or a curve. And then in neither discrete or continuous, some points are connected by a line or curve, but it is not continuous everywhere like in a continuous function. And then just remember the standard form of a linear equation is ax plus by is equal to c. So that concludes module 3.3. Have a great day, everyone.